James Hopwood JeansThe. The mathematical theory of electricity and magnetism. Quantity of electricity. 7. We pass next to the conception of a definite quantity of electricity, this quantity measuring the degree of electrification of the body with which it is associated. It is found that the quantity of electricity associated with any body remains constant except in so far as it is conducted away by conductors. To illustrate, and to some extent to prove this law, we may use an instrument known as the gold leaf electroscope. This consists of a glass vessel, through the top of which a metal rod is passed, supporting at its lower end two gold leaves which under normal conditions hang flat side by side, touching one another throughout their length. When an electrified body touches or is brought near to the brass rod, the two gold leaves are seen to separate, for reasons which will become clear later, so that the instrument can be used to examine whether or not a body is electrified. Let us fix a metal vessel on the top of the brass rod, the vessel being closed but having a lid through which bodies can be inserted. The lid must be supplied with an insulating handle for its manipulation. Suppose that we have electrified some piece of matter, to make the picture definite. Suppose that we have electrified a small brass rod by rubbing it on silk, and let us suspend this body inside the vessel by an insulating thread in such a manner that it does not touch the sides of the vessel. Let us close the lid of the vessel, so that the vessel entirely surrounds the electrified body, and note the amount of separation of the gold leaves of the electroscope. Let us try the experiment any number of times, placing the electrified body in different positions inside the closed vessel, taking care only that it does not come into contact with the sides of the vessel or with any other conductors. We shall find that in every case the separation of the gold leaves is exactly the same. In this way, then, we get the idea of a definite quantity of electrification associated with the brass rod. This quantity being independent of the position of the rod inside the closed vessel of the electroscope. We find, further, that the divergence of the gold leaves is not only independent of the position of the rod inside the vessel, but is independent of any changes of state which the rod may have experienced between successive insertions in the vessel, provided only that it has not been touched by conducting bodies. We might, for instance, heat the rod, or, if it was sufficiently thin, we might bend it into a different shape. And on replacing it inside the vessel we should find that it produced exactly the same deviation of the gold leaves as before. We may, then, regard the electrical properties of the rod as being due to a quantity of electricity associated with the rod, this quantity remaining permanently the same, except in so far as the original charge is lessened by contact with conductors, or increased by a fresh supply. 8. We can regard the electroscope as giving an indication of the magnitude of a quantity of electricity. Two charges being equal when they produce the same divergence of the leaves of the electroscope. In the same way we can regard a spring balance as giving an indication of the magnitude of a weight, two weights being equal when they produce the same extension of the spring. The question of the actual quantitative measurement of a quantity of electricity as a multiple of a specified unit has not yet been touched. We can, however, easily devise means for the exact quantitative measurement of electricity in terms of a unit. We can charge a brass rod to any degree we please, and agree that the charge on this rod is to be taken to be the standard unit charge. By rubbing a number of rods until each produces exactly the same divergence of the electroscope as the standard, we can prepare a number of unit charges. And we can now say that a charge is equal to n units, if it produces the same deviation of the electroscope as would be produced by n units all inserted in the vessel of the electroscope at once. This method of measuring an electric charge is of course not one that any rational being would apply in practice, but the object of the present explanation is to elucidate the fundamental principles, and not to give an account of practical methods. 9. Positive and negative electricity. Let us suppose that we insert in the vessel of the electroscope the piece of silk on which one of the brass rods has been supposed to have been rubbed in order to produce its unit charge. We shall find that the silk produces a divergence of the leaves of the electroscope, and further that this divergence is exactly equal to that which is produced by inserting the brass rod alone into the vessel of the electroscope. If, however, we insert the brass rod and the silk together into the electroscope, no deviation of the leaves can be detected. Again, let us suppose that we charge a brass rod A with a charge which the divergence of the leaves shows to be n units. Let us rub a second brass rod B with a piece of silk C until it has a charge, as indicated by the electroscope, of m units, m being smaller than n. If we insert the two brass rods together, the electroscope will, as already explained, give a divergence corresponding to n plus m units. If, however, we insert the rod A and the silk C together, the deviation will be found to correspond to n minus m units. In this way it is found that a charge of electricity must be supposed to have sign as well as magnitude. As a matter of convention, we agreed to speak of the m units of charge on the silk as m positive units, or more briefly as a charge plus m, while we speak of the charge on the brass as negative m units, or a charge minus m. 10. Generation of electricity. It is found to be a general law that, on rubbing two bodies which are initially uncharged, equal quantities of positive and negative electricity are produced on the two bodies, so that the total charge generated, measured algebraically, is nil. We have seen that the electroscope does not determine the sign of the charge placed inside the closed vessel, but only its magnitude. We can, however, determine both the sign and magnitude by two observations. Let us first insert the charged body alone into the vessel. Then, if the divergence of the leaves corresponds to m units, we know that the charge is either plus m or minus m, and if we now insert the body in company with another charged body, of which the charge is known to be plus n, then the charge we are attempting to measure will be plus m or minus m according as the divergence of the leaves indicates, n plus m or n minus m units. With more elaborate instruments to be described later, it is possible to determine both the magnitude and sign of a charge by one observation. If we had rubbed a rod of glass, instead of one of brass, on the silk, we should have found that the silk had a negative charge, and the glass of course an equal positive charge. It therefore appears that the sign of the charge produced on a body by friction depends not only on the nature of the body itself, but also on the nature of the body with which it has been rubbed. The following is found to be a general law. If rubbing a substance A on a second substance B charges A positively, and B negatively, and if rubbing the substance B on a third substance C charges B positively, and C negatively, then rubbing the substance A on the substance C will charge A positively, and C negatively. It is therefore possible to arrange any number of substances in a list such that a substance is charged with positive or negative electricity when rubbed with a second substance, according as the first substance stands above or below the second substance on the list. The following is a list of this kind, which includes some of the most important substances: cat skin, glass, ivory, silk, back crystal, the hand, wood, sulfur, flannel, cotton, shellac, caoutchouc, resins, gutta percha, metals, guncotton. A substance is said to be electropositive or electronegative to a second substance according as it stands above or below it on a list of this kind. Thus, of any pair of substances, one is always electropositive to the other being electronegative to the first. Two substances, although chemically the same, must be regarded as distinct for the purposes of a list such as the above, if their physical conditions are different. For instance, it is found that a hot body must be placed lower on the list than a cold body of the same chemical composition. 4. Attraction and repulsion of electric charges. 12. A small ball of pith, or some similarly light substance, coated with gold leaf and suspended by an insulating thread, forms a convenient instrument for investigating the forces, if any, which are brought into play by the presence of electric charges. Let us electrify a pith ball of this kind positively, and suspend it from a fixed point. We shall find that when we bring a second small body charged with positive electricity near to this first body, the two bodies tend to repel one another, whereas if we bring a negatively charged body near to it, the two bodies tend to attract one another. From this and similar experiments it is found that two small bodies charged with electricity of the same sign repel one another, and that two small bodies charged with electricity of different signs attract one another. This law can be well illustrated by tying together a few light silk threads by their ends, so that they form a tassel, and allowing the threads to hang vertically. If we now stroke the threads with the hand, or brush them with a brush of any kind, the threads all become positively electrified, and therefore repel one another. They consequently no longer hang vertically but spread themselves out into a cone. A similar phenomenon can often be noticed on brushing the hair in dry weather. The hairs become positively electrified and so tend to stand out from the head. 13. On shaking up a mixture of powdered red lead and yellow sulfur, the particles of red lead will become positively electrified, and those of the sulfur will become negatively electrified, as the result of the friction which has occurred between the two sets of particles in the shaking. If some of this powder is now dusted onto a positively electrified body, the particles of sulfur will be attracted and those of red lead repelled. The red lead will therefore fall off, or be easily removed by a breath of air, while the sulfur particles will be retained. The positively electrified body will therefore assume a yellow color on being dusted with the powder, and similarly a negatively electrified body would become red. It may sometimes be convenient to use this method of determining whether the electrification of a body is positive or negative. 14. The attraction and repulsion of two charged bodies is in many respects different from the force between one charged and one uncharged body. The latter force, as we have explained, was known to the Greeks. It must be attributed, as we shall see, to what is known as electric induction, and is invariably attractive. The forces between two bodies both of which are charged, forces which may be either attractive or repulsive, seem hardly to have been noticed until the 18th century. The observations of Robert Simmer on the attractions and repulsions of charged bodies are at least amusing. He was in the habit of wearing two pairs of stockings simultaneously, a worsted pair for comfort and a silk pair for appearance. In pulling off his stockings he noticed that they gave a crackling noise, and sometimes that they even emitted sparks when taken off in the dark. On taking the two stockings off together from the foot, and then drawing the one from inside the other, he found that both became inflated so as to reproduce the shape of the foot, and exhibited attractions and repulsions at a distance of as much as a foot and a half. When this experiment is performed with two black stockings in one hand, and two white in the other, it exhibits a very curious spectacle. The repulsion of those of the same color, and the attraction of those of different colors, throws them into an agitation that is not unentertaining, and makes them catch each at that of its opposite color, and at a greater distance than one would expect. When allowed to come together they all unite in one mass. When separated they resume their former appearance, and admit of the repetition of the experiment as often as you please, till their electricity, gradually wasting, stands in need of being recruited.